Full screen. So I'm calling this video from slope to implicit differentiation. How long it will take me, I don't know. I'm guessing 15 minutes max, but we'll find out. And then I'll say from slope to implicit differentiation in whatever it takes. All right, so let's go back in history. Let's start where math started. And I think it was probably somebody that went, put a mark on a cable. I don't know how many hundreds of years or thousands of years, but somebody came up with a symbol for a number and added a couple together, got a new symbol for the quantifying relationship. And addition and subtraction are born. All right, somebody saw 1 plus 1 is 2, and if this addition of 1 went to the other side, 2 minus 1 is still equal to 1. And then somebody said, 2 could be written as 1 times 2 with length times width, and area is born. I don't know when that would have occurred, but we certainly still use square area today for lots of different reasons, selling land and how much territory is burned in these poor fires. And it's all kinds of uses. So let's move through history some more here. These are all guesses on my part, obviously. I don't know for certain, but it would seem that at some point somebody added up a couple of numbers that equals 5 and said, well, what if we change the numbers? What if this column goes up by 1? Well, it looks like this column has to go down by 1. And then somebody probably said, well, how do we represent change? Well, letter X, which I believe in Arabic means the word something. That's what I heard on NPR. And I don't think NPR is trying to misinform me. I trust them. Trust all the news outlets now, but I trust them. And I don't think there's any conspiracies around that. Let's get out of politics and back to math. So if we pick X as something and random number, Descartes in the 1600s gave us this XY axis, and we pick random numbers on the X axis, and then, the Y values depend on what we're doing with that first number. There's lots of mathematical operations, so there's a lot of unsorting to do. But this is early on. And so X plus Y equals 5 is born. And they're products. I put them in as area statements. 1 times X is a product. 1 times Y is a product. And that was the first thing we talked about in class about 2-3 weeks ago. I don't know how long we've been together now, but it's a couple of weeks at least. I think we're in the middle of our third. And I asked somebody to tell me what 9.279 times 3.88888854921 is. And I thought you could give it to me in 1 second, and he said you couldn't. But if I said, what's 9.28 times 0? Well, you did answer that in under 2 seconds. So plugging a 0 in and using Descartes' little gadget here, if X was 0, Y is 5. And if Y is 0, X is 5. And we got 2 places. And then all of a sudden, we can look at all those other relationships where 4 plus 1 equals 5. And over 4 and up 1 seems to be on this. And they seem to line up. And all of a sudden, we're talking change in Y, change in X. The change in Y was -1. The change in X was 1 on those tables over there. And some French guy gave it the word slope, I think, in the 1800s. And so all of a sudden, if we know we can move one of the numbers to the other side, somebody came up with the dependent numbers come from -x plus 5. And mx plus b is born. And I wish we weren't working with mx plus b so much just because. All right, so did I want to say anything else there? No. So let's move in history a little bit more. And after somebody, I'm guessing again, x plus y, well, somebody maybe did 2x plus 3y. Got a new sum, 6. And maybe took it over to the other side, then divided by 3, and there's our mx plus b. And you can check numbers by plugging them into what changed to functional notation. Okay, so somebody decided that if you plug a number in here, you got to do the math to get the number on the left. Well, wouldn't it be nice if we could stay from left to right, because that's how we read? So somebody said, well, let's let our x equal 9. What's our y value going to be? F of 9. F of 9 means use the 9. Find what you get. And 3 goes into 9 3 times. 3 times -2 is -6 plus 2, -4. And it follows our pattern, because if this is a product, we should put a 0 in, and 0, 2 gets us the y-intercept. which I think is far less important than the x-intercept, and I'll talk about that in a moment. But we've got functional notation. We've got something called standard form. That's what this is. I guess I wrote it over there. This is standard form. And I've been asking you on tests to give me the two numbers that standard form is based on. And it's based on the intercepts. Let x equal 0, y is 2. Let y equal 0, x is 2. X is 3, excuse me. That's not hard. And if you pay attention, the sum of these two variables gives us a decreasing function at a -2 to 3 rate because we can see it. And I'd like you to see it. That's up 3 on the left, down 2 on the right. All right. And our slope was -2/3. So if a 0, x gets us a 2 for a y, 6/3 is 2. And if I go down 2/3, I keep going down 2/3, eventually I'm going to get to 9, which is -4 here. You can keep counting. You'll see it's true. And then we get some user-friendly numbers. I think 0, 2 is friendly. I think -6/3 is 2. So 6 and -2 work. And somebody came up with point slope form. Point slope form is taking a point like 6, which is an x value, getting rid of it, making it a 0, setting our right to 2, y -2. That gets me correspondence right here. And then somebody said, oh yeah, and we're going down at a -2 to 3 clip. I could start measuring from the point 6, 6, -2, 6, +2. I could start measuring from there. And if I did, 0, 2 is here, 3, 0 is here, 6, -2 appears to be here, you know, it's lining up. So I could measure from a place like that. Of course, in my class, you know, we do the next linear function, which is bringing the -2 to the other side. And I think that is usually helpful. Why is it usually helpful? Because then we can start seeing some other patterns. Right? So let's just play with this for a moment. 2x plus 3y. I could divide by 3 to get the slope intercept, but I should also factor out 2/3, -2/3. What did I factor out? -2/3 times that. So I need this to be, I don't want to stop. I might have made a mistake here, so I'm just going to stop because when I do that, I have to start over again. I don't want to. But I like this form because if we morph it into the quadratic, in case I got a signer there, I'm not going to deal with it. If I make this into a quadratic, that's the linear. It turns out all I'm doing is putting a squared here and a squared there. A squared here and a square there. And I can begin to see the linear to the quadratic to the square root. Very similar here, because the only thing is operational change. When I drop a 9 here, I get 3 operationally. That's what I have to cancel. When I put a 9 in here, I get 9 - 6, 3 squared. That's what I have to cancel. When I put a 9 in here, I get the square root of 3. That's what I have to cancel in order to get to -4. In order to get to -4. In order to get to -4. And that even works for cubics, which is a lot more complicated, but not terribly complicated. So I'll hold that there for a second. If you want to learn how to do cubics in graphing form, then you got to really look at one of the videos on the cubic side of things. But what you'll find is, and I'll move this down, what I'm trying to show by this factored situation is that -b/a gets you the x-intercept. And so ax plus b, if I factor that, I get a times x minus, ax plus b, a times x plus b. Okay, and when does that equal 0? -b/a. Oh, that's what I wanted to say. So I didn't make a mistake over there. I just lost track of where I was. And that gets you an x-intercept. And it also knocks down this to one term. That's one term. If you use -b/2a, the graphing form, I guess I'll write it again. The graphing form, if we write b/2a here, and we use -b/2a, well, that's 2 terms instead of 3. ax squared plus bx plus c. Right? That's what quadratic is, 3 terms, but getting it down to 2 is helpful in a graphical sense and a numerical sense. It's easier to work with. Minus b over 3a turns out to be what you work with in a cubic, and that gives you the point of inflection. Minus b over 4a does not seem to have graphical significance as a point to measure from, but it does allow you to rewrite this in, instead of 4 terms, in 3 terms. So it's easier to work with. All right, so what came next? All right, we're almost getting in implicit differentiation. Taking a little longer than I thought. Said a few more things than I thought I would. Well, 1 times x plus 1 times y equals 6 or 5. That's kind of where we started. But somebody said, well, what if we make them both sides variable? Okay, and let's set this to 25 because I want to make some easy numbers to work with. Well, what do we get? We get x squared plus y squared equals 25. Well, wouldn't zeros be helpful here? If you plug in 0, what do you get for y? Most people say 5. And most people forget to say -5 because they discriminate against negative numbers. And what if y was 0? Well, you get 5 and -5. And what might be one of the most famous Pythagorean relationships, because that's what you're looking at, x, y, and 5, and therefore x squared plus y squared equals 5 squared. Right, that's what we're working with. Well, why wouldn't we put zeros in? We would. But what other numbers are really famous here? 3 and 4. 3 squared plus 4 squared equals 25. So 3, 4 also works. 3, 4 works. So does 3, -4. So does, well, 3, -4 is down here. So I guess I got to move that. 3, -4 is there. All right. And so does -4, 3 be here. So would -4, -3 be there. I hope you're starting to see a circle. Now, it'd be hard to see the circle if I did a graphical. It's an interesting conversation. X squared plus y squared equaling 25. Well, I think that's worth a video sometime. There's a lot to talk about there. Domain restrictions, which we have over here. I can't get bigger than 5. If I make a number bigger than 5, you tell me what I square to get 25. I think it's outside the domain range, the domain interval. And if I did the same thing with the y's, made y 6, I think it's out of the range interval. We got to stop talking about domain and range restrictions. Okay? This would be a complicated conversation. I encourage you to think about how would you go about doing x squared plus y squared. I kind of give the answer with the implicit differentiation, but I won't say anything about it. All right, so where does that lead us? Well, it leads us to what we're working on in class for the first time today. What if I said I want this to equal, hang on, 9, 25, 34. Oh, let's say 25 again. It's okay. I don't want to mislead, but I could have written that. Then what do we do if we want to see these numbers interact? Well, we got to turn them into squares. And that's why we're learning to do what? We're learning to do, I don't think I have to do that over here. I just talked about it. What we're learning to do is to rewrite this, which is a rectangle, x times x minus 6, into a square by writing x minus 3 squared minus 9. And we've been talking about this for several days now. As to why, that's the same calculation as that. I won't belabor the point here, but I also could have done the same thing here, evening off the sides of the rectangle. Minus 25 equals 25. It's not what I was looking for, but it's okay. Yeah, it is what I'm looking for, because that's going to, okay. Did I miscount? 25 plus 9 is 34. 34 and 15 is 49. So I want this to be a nice round number here for you. So now, if I add 25 and 9 to that, now I get 49. Okay, I'm not going to start again. And so what do I have? If I move everything, I get x minus 3 squared plus y plus 5 squared equals 49. And I get a triangle whose side is x minus 3, whose other side is y plus 5, and whose other side is 7, because when I get the squares, there's the 7 squared. When I get the squares, There's the x minus 3 squared should be inside. Same thing here, the y plus 5, I missed the bottom there, but, right? And that's what you're looking at, the square area is adding up. And as this square gets bigger, that one's got to get smaller, and this is still a circle. But the question is, where is it centered? Where is it centered? Well, this is x minus 3. What if I pick the random number 3 for x? Well, there's nothing coming out of that linear. So everything's got to come from the other side here. Everything's got to come from that. So I got to go up 7 units from what? From 3. So 3 comma, well, I got to find the y value that I'm at. So what was it? Y plus 5. So 3 negative 5 turns out to be the center of your circle. And I got to go up 7 units from negative 5. And that takes me to 2. Those numbers should work here. Let's look at it. 3 minus 3. Same thing we did with the standard form. We made it a 0. And then it's easy to see that, yes, 2 works. And we'll be studying that more. I'm not going to do that now. Already got videos up for circles. It's called running around in circle. You can see that, get practice. But we're going to implicit differentiation now. And so for those of you who are already studying calculus, hopefully this will make some sense. But we looked and I gave you a handout. I gave you a handout and, no, I guess I'm over here now. I gave you a handout where I drew squares. I looked at how squares change at an instant. So I'm using 0.001 as a little amount of time elapses from hour 3 to 3.001. And what's my dependent values? They're over here, 9.00601. And remember, for y squared, 25 minus x squared, I could have moved the x squared to that side. If I write it as a function, I get the square root of 25 minus x squared, which means that if I change this by 0.001, right, the y value is going to change in a certain way so that I get correspondence here. Now, what happens if I change the y value by 0.001? I get 0.008 for change. Over here, I get 0.006. Well, if I don't want my 25 to change in this squaring process, then when I add these things up, I can get no change over here. It can be no change. So what do I have to do to 0.008? To turn it into negative 0.006, because that's what I need. I need negative 0.006 from this other term. Otherwise, my number's not going to be 15 anymore, or whatever I started out with. And that's why I gave you triangle times 3 equals W, and I think it was a Greek letter. But somebody just wrote to me from Greece. I'll have to ask him, all right, how to pronounce it. All right, and I tried to get your brain out of 3 times what equals W. That was the purpose of it. So that you could really say, I don't want a 3. Let me cancel it out of the problem. I want that W. So I don't want this 0.008. I'll get rid of it. I want negative 0.006. And if you look at that, you get negative 6/8, which happens to be negative 3/4. And what numbers did we start with? An x value of negative 3 and a y value of 4. So let's go back here and let's look at negative x over y and talk about a ratio of change at that instant. Let's look at some of those other instances for just x squared plus y squared equals 25. Okay, so what is negative x? If I use 0.5, what is negative x over y? It's minus 0/5, which is 0. And guess what the slope of the tangent line is there? It happens to be 0. Nice coincidence. At 4,3, we're going down at 4,3, at 4,3. So let's just change it here. 4,3. Well, isn't that minus 4/3? Is it believable that I might be going down at a little bit more than, a little bit more than 1 to 1 right here? If I drew it well. And what if I had 5, 0 here? 5, 0. Well, wouldn't I have minus 5/0? Correct me if I'm wrong, but I think that's undefined. And what would the slope be? It would be straight up and down. And guess what? The slope of a vertical line is undefined. Seems like we've got something that's giving us rate of change, which is a ratio of change, which is what M is. It's a ratio of change. It just happens to be the easiest one to understand. But as we go further up in mathematics, we're looking for rates of change for e to the x, ln of x, square root of x. That's what that next level of study is that awaits you. So therefore, I think you have to have a certain foundation before you get there. Now, I will actually do the implicit differentiation for you carefully and quickly, or I'll try to right here in a second. But what I did was I did 3 by 3, and these relationship between differentiation and integration will do a better job of explaining what I'm explaining now. And related rates. In the related rates, in the calculus playlist, I'm sure there's a related race about implicit differentiation. And it really talks about the 3 by 3 and the 4 by 4, and it plays with the layering situation, which is really a 2x situation. So I'm not going to get into it much more right now, but for the calculus people, the rate of change of x squared is 2x dx, right? Well, that's the change in y. Right? That's the change here. Look at those other videos. This is 2y dy, and 25 is not changing. If you see that number change anytime in the next 2 minutes, call me. Write me an email, I'll help you out. So how do we get the change in y or the change in x in the calculus concept? We divide by dx. We divide by dx. We do a little algebra. And if I do that, I have it right there. These cancel, so I'll move the 2x to the other side. That gives me 2y times dy dx. And all these values do work. Equals minus 2x. And so how do I isolate dy dx? Little multiplication, dx, little division by 2y on the other side, minus 2x over 2y. And there's our minus x over y. There's a little bit of implicit differentiation, shortcutted quite a bit at the end, but that's not the level class I'm teaching. But I think it's important to plant some seeds. Otherwise, when you get to calculus, you don't have much time to understand that, a couple of days at best. And I'm not sure the brain processes it. So you're seeing it, it's in your brain whether you want it or not, because you just saw it. So there's a Rolodex in there, and it's there somewhere. All right, so it won't be the first time you see it. How long did it take me to do this? Longer than I thought, but hopefully it's a decent discussion, and maybe it clarifies some things. I don't know. It's what I'm trying to do. Hey, have a nice day. It was minus 10 degrees here today. Oh well, that was the morning. It's a little warmer now. Hope it's a little warmer where you are. Not too much though. We got a problem with that. All right, bye-bye.